When we have a mass attached to a spring, either in a vertical or horizontal position, like I've drawn here, we can set it oscillating back and forth by compressing or extending the mass spring system. Now, if these systems have the same mass, for example, 0.5 kilograms, and the same spring constant, and the spring constant is essentially the stiffness of the spring. So the higher the spring constant, the stiffer the spring. So if we got the same mass and the same spring constant, both these mass spring systems will have the same period of oscillation. So the time it takes both spring systems to compress fully, extend, then arrive back to their equilibrium position will be the same. Gravitational acceleration will not affect the vertical spring's oscillation. So the formula for the period for this type of system, this type of oscillator, is the period is equal to 2 pi multiplied by the square root of the mass of the spring divided by the spring constant. There is no term for the gravitational acceleration in this formula. And so this indicates that it doesn't matter which direction or which gravitational field your mass spring system is in, they're going to oscillate at the same rate so long as the mass and the spring constant is the same. So let's start with our first question. A mass of 0.30 kilograms is attached to a spring and is set into vibration with a period of 0.24 seconds. What is the spring constant of the spring? So I'm going to draw this out quickly just so we can visualize this more easily. Now I put the mass spring system in a vertical position, but it doesn't matter whether it's in a vertical position or horizontal position. And it doesn't even matter what planet we're doing this on or whether we're doing this on the moon, because the gravitational acceleration doesn't matter in this case. So do you think we have enough information here to use our formula for the period for a mass spring system? Well, we have all the values for the variables except for the spring constant, but we need to transpose this equation so that we can isolate the spring constant on the left-hand side. So let's start by removing the square root on the right-hand side. Now we do this by squaring both sides of the equation. So we got t squared is equal to 2 pi squared multiplied by the fraction of the mass divided by the spring constant. Now to move the spring constant to the left-hand side of the equation, we multiply both sides of the equation by the spring constant. This cancels out the spring constant on the right-hand side and leaves the spring constant on the left-hand side. Next, we divide both sides of the equation by the period, so we can shift the period squared over to the right-hand side. And this now isolates the spring constant on the left-hand side. So we've got the spring constant is equal to 4 pi squared multiplied by the mass of the spring mass system divided by the period squared. And if we plug in our numbers now, we get a spring constant of 2.1 times 10 to the power of 2 newtons per meter, to two significant figures. So question 2. A 125 Newton object vibrates with a period of 3.56 seconds when hanging from a spring. What is the spring constant of the spring? So again, let's draw out a problem. So our mass spring system is now in a vertical position. And again, the gravitational acceleration does not have any effect on the period of this oscillator. And this mass spring system will oscillate according to our formula. The period is equal to 2 pi multiplied by the square root of the mass divided by the spring constant. And again, this is true no matter what the orientation of the system. So we're given the period, but we're not given the mass or the spring constant. So how can we find the mass value? Well, our question says that our object has a gravitational force of 125 newtons. So what does this mean here? So all masses experience a gravitational force within a gravitational field, and this gravitational force, Fg, depends on the mass of the object and the gravitational acceleration of whatever large object it happens to be placed on. So for example, the Earth. So even though this question hasn't specified which planet this mass spring system is on, let's assume it's on the Earth at sea level, where the gravitational acceleration is 9.81 meters per second squared, accurate to 3 significant figures. So we've already been given our force due to gravity, 125 newtons. So we can find the mass by rearranging this equation. And the mass is equal to 125 newtons divided by our gravitational acceleration. We get 12.7 kilograms to 3 significant figures. So now, like we did with the previous question, we can rearrange our period formula to isolate the spring constant. So instead of doing this again, I'm just going to use the previous transposed equation, which is the spring constant is equal to 4 pi squared multiplied by the mass divided by the period squared. Once we plug in all the numbers, we get a spring constant of 39.7 newtons per meter. And the higher the spring constant, the stiffer the spring. So the very last question, we've got a spring with a spring constant of 30.0 newtons per meter, and it's attached to a mass of 2.3 kilograms, and the system is set in motion. Find the period and frequency of the vibration for this mass. So I'm going to draw this up again, and it doesn't matter whether our spring mass system is in a vertical position or horizontal position, but I'm going to draw it in a vertical position here. We've got 2.3 kilograms oscillating about this equilibrium position, and we've got a rather stiff spring with a spring constant of 30.0 newtons per meter. So do you remember what our equation is for the period for this type of oscillator? So the period is equal to 2 pi multiplied by the square root of the mass of the oscillator divided by the spring constant. If we plug in our values, we get a period of 1.739735 and so on. But because our mass is only accurate to 2 significant figures, then our period can only be accurate to 2 significant figures as well. So our period rounds down to 1.7 seconds. But I'm going to store this value on my calculator so we don't get any rounding errors when we're calculating the frequency. So how can we find the frequency of an oscillator given its period? So in order to get the frequency, we invert the period. So the frequency is equal to 1 divided by the period. So 1 divided by our value on our calculator, so that would be 1.739 and so on, gives us another number with a lot of decimal places, 0.5748 and so on. But because our mass only has 2 significant figures, our frequency can only be accurate to 2 significant figures as well. So our frequency is 0.57 hertz, or seconds to the minus 1, to 2 significant figures.